And we thought that nothing could be simpler than we let you know how to separate two liquids that are mixed together based on their boiling points. So basically, what is distillation? When we say distillation, we mean that we take a liquid and we boil it, and somehow by boiling we convert it to vapor, and somehow we cool the vapor and collect the vapor to get the liquid back. So we can evaporate the liquid at the boiling point, and then we can condense it by cooling the vapor back into liquid. That's called distillation. Like rain is distillation, because water is evaporated from the oceans and it comes back in the form of rain. That's also a nature's way of distilling water. So if we have two liquids that they differ more than 40, 50 or 70 degrees in boiling point, then we can actually separate them reasonably, not purely, but not completely, but basically to some extent we can actually separate them. The larger the difference in boiling point, the easier it is to separate the components of the mixture. So we are actually trying to separate the components of binary liquids. Binary means two liquids, right? Liquids based on their boiling points. So here today we'll be using hexane, which is a lower boiling component. It boils at 69 degrees Celsius, and toluene that boils at higher temperature, almost 111. So we'll be giving you one-to-one mixture. These are soluble completely, they are miscible, and we'll give you the mixture. We are asking you to separate them. So basically, how do you separate them? Based on based on two laws. First law is Dalton's law of partial pressures, which means that when you boil a mixture of two liquids, then their vapor pressures, the individual vapor pressures, are added together to get the total vapor pressure. The total vapor pressure is equal to the vapor pressure of individual components. So if there are two components A and B, the vapor pressure, total vapor pressure would be P is equal to PA plus PB. PA is partial pressure of A and PB is partial pressure of B. So that's the Dalton's law of pressure, partial pressures. And the other law that we are going to make use of is Rolle's law. Rolle's law is basically the partial pressure of A is equal to the total pressure of pure liquid A multiplied by the mole fraction of A. Mole fraction of A is the moles, number of moles of A divided by number of moles of A plus B, if there are only two components. So you can roughly correlate it with percentage volume by volume. Percentage volume by volume almost equal to same thing in terms of mole fractions. Anyway, so you look at this graph. So these are the boiling points of different mixtures. Mole fraction of toluene is 1. That means pure toluene. If you pure toluene, it boils at 110.6 degrees. And when you are mixing it like this, you can add 10%, 20%, 30%, 40%, etc. You can keep adding hexane to it. You increase the amount of hexane, then here you will be getting pure hexane, right? So pure hexane boils at 69. So these are different boiling points of different compositions. Alright, so these are boiling point curves, and this curve that joins together is the vapor pressure. This is Dalton's law of partial pressures. Total pressure is equal to partial pressure of hexane plus partial pressure of toluene. Now let's discuss how to set up this apparatus. Now the manual says that you take a 100 ml flask, RB flask. RB means round bottom flask. Yeah, we are taking this round bottom flask, and according to the manual, you take this distillation adapter and you join it directly here. But my experience is that if you interpose between the round bottom flask and the distillation head another condenser. You have two condensers in the kit. Now you use the one that has a bigger inner channel. Both are best condenser, the bigger inner channel, and you interpose it to make the distance longer. So when you boil the mixture, the vapor will have to travel a long distance, and when they longer the distance, they have a better chance of separation. So that was my idea, and when I did it, it turned out to be much better actually. So I asked my students actually to interpose another column here, dry column, no water running through it. Now you'll be using another condenser here, so you'll be using both condensers today. Okay. So you have this distillation head, 3-way connector. You connect it with a thermometer adapter and you insert a thermometer. Now thermometer should be inserted in such a way that the bulb of the thermometer should be a little bit below this level. Okay. Now you connect it with another. This is the water condenser. Now here the water should be going in from the lower end and should be coming out from the upper end. And at the end you have a distillation adapter with a side tube and which is attached to a 25 ml round bottom flask. Round bottom flask. Okay, you use two lap stands, iron stands, one for this 25 ml round bottom flask and the other for the rest of the apparatus. So this is set up your apparatus, and this is the heating mantle because you want to heat it. Of course, this heating mantle is connected to a thermo temperature controller called Variac. So you use that as well, and you keep it about 50 setting, okay, when you start it. So make sure your distillation is slow and steady, not too fast. How can you tell it's too fast? Because when the liquid is coming too fast, you can find out from the number of drops that are coming from the other end. Ideally, it should be only one drop a second, okay? You want to make it slow and steady, not fast. Okay, because a lot of people get impatient, and when they get impatient, then they get bad mixtures here. And remember, you want to separate the components as much as possible, right? You want to get it as pure as possible. It won't be 100% pure, but of course 90% is better than 80%, 80% better than 50%, something like that. So make sure your distillation is slow and steady. You have to control the temperature really well. Okay, so and then this thermometer is measuring the boiling point. So you will see that the first drops that come out, they are close to 69, because remember, 69 is the lower boiling component of your mixture, which is hexane. Okay, toluene boils at 110. So obviously, the lower boiling comes out first in higher concentration. But by the time it reaches here, so hopefully it will be absolutely pure. Okay. All right. So we will collect the fraction as long as it is coming at 69 degrees Celsius. It should be almost constant. Then at some point it will start going down. That means that most of the hexane is out. Now you want to actually heat the mixture further. So from 50 to increase the setting to 70 maybe, or 70 or maybe more. And now you are heating it more. When you heat it more, now the toluene is the turn of the toluene to come out now in higher concentration. So you will see that the temperature now is going beyond 69, right? Because now the vapor of toluene is increasing. So you collect the fraction that comes out between 69 to 90 degrees Celsius. So it's like a big range. You basically collect that fraction, and after that, remember when you start, when the temperature goes down from 69, you remove the flask, okay, and then insert another flask, and that second flask should be collecting 69 to 90 degrees liquid. This liquid will have more toluene there, right? So there will be second fraction. That's all. Once you do that, your experiment is done. Then you basically you turn the temperature off, start cooling everything, cooling the pot. This is the distilling pot. Now some of the liquid will remain behind here. Okay, mostly toluene. Remember, mostly toluene will remain here. Now you have now three things you have collected. First fraction, second fraction, first fraction around 69, second fraction between 69 to 90, and the third fraction will be, you don't have to collect it, it's remaining behind, right? Now what you do is basically you want to find out the densities, okay? Now you want to find out the percentages. You know what's the percentage of hexane in the first fraction? What's the percentage of hexane in the second fraction? And what's the percentage of hexane in this remaining? Right? You want to find out the composition, and there are two ways to do that. I found out that the first way is to find out the refractive index. We can measure refractive index. We have Abby's refractometer available in this lab, so I encourage you to use that. That'll give you more accurate results. And in my video, I have actually described to you how to use that Abby's refractometer. Okay, so you can measure the refractive indices of these three solutions, and or else alternatively you can measure the density. How do you can measure the density? Take the first fraction and add about 1 mil, exactly 1 mil in a graduated cylinder, 1 mil, and weigh the graduated cylinder first, and then add about 1 mil of the first fraction, and then find out the mass. Okay, that would be the mass of the first fraction, 1 mil of first fraction. That will give you the density. Okay. Also, you can measure. You should measure the 1 mil. Measure 1 mil of the second fraction and find out the density for that, and also measure 1 mil of that and find out the mass of that as well. So you'll be at three masses. Three masses are also densities because you are taking 1 mil. The density is equal to mass divided by volume. Volume is 1 mil, so mass is the same as density in this case. All right, so now you want to find out what's the percentage. You have found the density, you have found the RI, refractive index. So basically, you will be given 5 solutions in the lab. They will be available. Okay, the instructor will prepare it for you. Well, first is the pure hexane. Second is pure toluene. Okay, and the mixture that the instructor will be making 3, 75% and 25%. 75% hexane, 25% toluene, volume by volume. Similarly, 50-50 and 25 to 75. Okay. All right. So these are known compositions. Okay. So what you can do is you can use some Excel program in your computer, and you can draw a nice curve using scatter plot. You plot density, composition, composition, percentage composition on the x-axis, and density or refractive index on this coordinate y. Okay, you can find out. So you will see that you can make a standard curve. We call it standard curve, right? Now you know what the Ri value or density value of your first fraction or second fraction or the distilling pot, the leftover liquid in the distilling pot. You have already measured those values, so you can find out actually the values using this standard curve. You know that the equation of the linear equation is y is equal to mx plus b. Y and x are variables, so this is the refractive index or density, and this is the percentage composition, and m is the slope, and b is the intercept. Okay, these values m and b are given by the computer, so you don't have to worry about that. So it will give you can only find out the value of x. You know the y, you know m, you know b, and find out the value of x. All right, so let's go head to the lab and find out the experiment. So we are back here in the lab, and let me describe to you the components of this experiment. The two liquids are toluene, which is a higher boiling, and the hexane, which is a lower boiling. The difference between the two is about 42 degrees Celsius. And this is 1-to-1 mixture, 50-50 mixture of toluene and hexane. This is the one that we are going to actually separate the components of. So that's the mixture that we're going to be charging the round bottom flask with. And this is the condenser. We'll be using two condensers, one with the inner tube wider and the other with the narrower inner tube. And this is the 25 ml round bottom flask, and the other one is 100 ml round bottom flask. And this is the three-way connector, and three-way connector has fitted with it thermometer adapter through which the thermometer goes, and the lower end of the thermometer should be close to the lower end of the three-way connector to get proper temperature. And this is the other condenser with a narrow tube inside. So water goes from the lower end to the upper end and exits from the upper end. This is the three-way connector, thermometer adapter, and thermometer, and the vapor. Well, I'm just adjusting the bulb of the thermometer a little bit lower than the connection of the three-way connector. Okay, so we are ready now. This is the vacuum adapter. Vacuum adapter is fitted with 25 ml collecting flask. Okay, so we have the entire entire apparatus setup. We have already charged with the 1-to-1 mixture of hexane and toluene. Now we are going to heat it. Make sure that the setting is around 80 setting. 80 setting is appropriate to boil the first component, which is a hexane. So hexane should boil around 69, and so that's at least that's the hope. Okay, so we are ready to heat it. We are heating it now, and hopefully the vapor will rise through the first condenser, air condenser, and it will be condensed at the very end and will be collecting into the collecting flask. Okay, it looks like our modification of interposing an empty condenser between the round bottom flask and the three-way connector worked really well. I can see the temperature is almost constant. It has been like that around 69 for a while, and so I'll collect the distillate between the temperature 69 to about 71 or 72, and while keeping the variac temperature around 80, and because it's really working really well. Now this is the second fraction of the distillate that I have collected in the 25 ml round bottom flask, and this fraction is between 73 Celsius to all the way to 99 degrees Celsius. And so this is a fraction between 73 to 99, and this should have a little bit less hexane compared to the first fraction. First fraction was between 69 to 73. 69 to 73 must have almost pure hexane. This one is between 73 to 99. So this is the second fraction. I have actually finished the experiment, so I'm going to basically turn the water off and turn the heat off, and collect remove this flask. So there are three fractions now: first fraction, second fraction, and third fraction in the pot. I want to make a standard curve. For that, I have pure toluene, pure hexane, and this is 75% hexane, 25% toluene, and this is 50-50 hexane and toluene, and this is 25% hexane and 75% toluene. These are three solutions that we have made to make sure that we have a standard curve made
we are going to measure the refractive indices of all these fractions, and we will also be measuring the refractive indices of the three fractions that I have collected. Okay, now we are going to measure the refractive index of all the fractions. The first fraction and the second fraction and the liquid that is left over in the pot. Also, I want to measure the refractive indices of the known solutions, hexane, toluene, and the three percentages that I showed you. Let me describe to you the features of this Abbey refractometer. This is an instrument that measures the refractive index. This is a main knob by which you can actually uh, you can adjust a line that meets the crosshairs, the middle point of the crosshairs. And these are two prisms that are sitting on top of each other. What you want to do is you put a couple of drops on the lower prism, the drops of the liquid that you want to measure the refractive index for. And you put a couple of drops there, and this is basically the liquid leftover, unknown liquid that was left over in the pot when we stopped the distillation. And we put a couple of drops on top of the lower prism, and close the upper prism on top of it. Make sure it clicks closed. Alright, and now you turn the light on, put the light up into the eyepiece. Through the eyepiece you can actually see the crosshairs, and you can also see a shadow that should be a black shadow. So basically this view should be just black and white. However, there are some colors, rainbow colors, and you want to remove those rainbow colors by adjusting the fringes. That's what I'm doing right now. I'm adjusting the removing the colors. Okay, removing the fringes, and I'm using this adjuster. This is the knob, the main knob, that actually you can move the shadow up and down so that the shadow moves in the middle of the crosshairs. Now it's very difficult for us to show you what is going on inside the eyepiece. However, we have to basically just believe us. Okay, after you have measured the refractive indices of all the fractions, the pure hexane, pure toluene, and all the known fractions, you can make a standard curve. And this is the standard curve that we have made. I've measured on the red, I have measured the refractive indices of all those known fractions. And I've also measured the refractive index of the unknown fractions. Now, the known fractions can be used to to form a standard curve. You can use Excel program to do that. Percentage composition on the x-axis and the refractive indices on the y-axis. You could also make the same curve, same type of curve in the density versus percentage composition as well. And some of you may want to do that, but I think finding out the refractive index is a lot easier and more accurate compared to the density versus composition curve. This curve is also okay, but it's less accurate compared to the refractive index one, this one. So you can actually draw a curve in the Excel program using scatter plot. Scatter plot will give you a trend line that give you a linear equation. Y is equal to mx plus b, and you can find out y and m as needed.